So this video is a continuation from Chapter 3 in Chemistry 2045. It's going to focus primarily on molecular weights, mole problems involving molecules and compounds, grams the moles, grams the molecules, that kind of thing. It is really a continuation of Chapter 2 when I went over grams and moles for atoms. You also find the same information in Chemistry 1025 videos, specifically in Module 7. The video is also going to focus on empirical molecular formulas. You'll find that in Module 8 from Chemistry 1025. I should point out right now that the section on empirical molecular formulas, there's going to be something new in this chapter that I did not cover previously in Chem 1025, and that deals with combustion analysis and find the empirical formula of a hydrocarbon. So that part will be a little bit different. So I want to mention that now, so that if you're watching this video, if you want to skip through some of it, that's okay. Make sure you watch the part on the end regarding combustion analysis, because that will be different and is new. Alright, so last video I focused on nomenclature. You can see on this flow chart shows how to name compounds and write formulas based upon whether something is not simple, an ionic compound, only metal, non-metal. We have the type 1 metals where we only form one particular charge. We have the type 2 metals where we use Roman numerals to indicate the charges. We have these molecular compounds which involve two nonmetals. This involves the prefixes for the different nonmetals to indicate the number of each nonmetal. And the last thing we talked about, we dealt with acids, whether it's a binary acid involving having the word hydro in the front, or whether it's a oxyacid, typically involving the polyatomic ions. These either end in IC or OUS, depending upon what the polyatomic ion ended in. So 8 turns to ic and 8 turns to aus. So if any questions about this, please make sure you go ahead and watch my previous video on this chapter, as well as my Module 5 video from Chemistry 1025. So then basically going forward, we talk about moles, something called formula mass. So formula mass is also known as molar mass. You might hear these words, similar wording for this. So formula mass, molar mass, molecular weight. Technically, molecular weight involves molecules, where molar mass is more general. So molecular weight means like molecules, but for things like something that's ionic, like sodium chloride, really sodium chloride is not a molecule. It is a compound. So molar mass or formula mass are actually more appropriate terms. I will use these sort of interchangeably, so I'm not going to make a big deal about it. So if you hear the word molecular weight, just do the same thing we do with any of the other terms. So basically the idea here is in order to find the molecular weight, we just add up the parts. So for example, in the case of water, H2O, we have 2 hydrogens, and we have 1 oxygen. You check the periodic table, you find oxygen, which is 16, you find hydrogen, which is a 1.01, add them all, do the math, you get 18.02 AMU, so that is atomic mass units. And just like back in Chapter 2, or Module 7 from Chem 1025, 18.02 AMU, that is equivalent to 18.02 grams per mole. So it ends up being the same. So let's try a couple other examples for this, just to make sure we're clear how to do this. So let's say we got something like H2SO4, sulfuric acid. H2SO4. So we have 2 H's, so it's going to be 2 times H. I have 1 sulfur, so 1 times S, and 4 O's, so 4 times O. So 2 times, you check the periodic table. Hydrogen has an atomic weight of 1.01. I know it's hard to see in this table, but you can go ahead and check yours. It's 1.01. 1.01. You have 2 of them, so it's going to be 2.02. Sulfur's over here is 32.06 in this table. So 1 times 32.06, that's just 32.06. And then oxygen is going to be 4 times 16. So 16 plus 16 is 32. Double that is 64. Add these all up. Now the units for this are all going to be grams per mole. Grams per mole for all of this. So we get 64 plus 32.06 plus 2.02, that's equal to 98.08. 98.08 grams per mole. So if I asked you on the test or something, what's the molecular weight or what's the molar mass or what's the formula mass, this is what I want you to do. So that's that example. Let's try something involving parentheses. Make sure you're okay with how to handle that. Again, if this is something that you're familiar with, if you want to skip ahead, you certainly may do so if you just fast forward in the video. But I want to make sure you're all comfortable with this. So maybe we're talking about, say, NH4 parentheses 2 SO4. So it's ammonium sulfate. So when you have parentheses here, you have to remember this is like having one nitrogen. So it's going to be 2 times 1 and then 2 times 4. So we have to remember to distribute this through. So we have N, we have H, we have S, and we have O. So we have 1 times 2, so that's going to be 2 times nitrogen. Nitrogen has an atomic weight of 14.01. That's going to be 28.02 grams per mole. Hydrogen, let's see, so 4 times 2, that's 8 of those. So 8 times 1.01, that is 8.08 grams per mole. So again, these are all grams per mole. Sulfur, from the previous example, we have 1 of those, so it's 1 times 32.06 grams per mole. That's just 32.06. Oxygen 16. 16 times 4 is 64. So 4 times 16.00 equals 64.00. Add these all together, and that will now tell us the molecular weight of ammonium sulfate. 28.02 plus 8.08 plus 32.06 plus 64, and that is 132.16 grams per mole. Now when we do these, just like the previous chapter, we're going to keep 2 decimal places in all these atomic weights. Okay, I'm going to round the 2 decimal places, and for purposes of sig figs, I'm going to assume that this is an infinite number of sig figs for calculations later on. We can always find a periodic table with more digits. I'm just using 2 decimal places here because that's good enough for most of our calculations we'll be working with. Do something involving a hydrate now. So maybe it's copper 2 sulfate pentahydrate, a very common hydrate. Copper 2 sulfate, that's going to be CuSO4. Remember, sulfur is a -2 charge, copper has to be a +2 charge, so that gives us copper 2 sulfate. Pentahydrate means dot 5H2O. So pentahydrate. Alright, so we have copper, we have S, we have O, and we have H. You can do this a couple different ways. I'm just going to break them down this way. Doesn't make any difference really. So it's 1 times copper. Copper, I believe, is 63 and point something. Copper's right here. It's atomic number 29. So that's 63.55. 63.55 grams per mole. We have 1 sulfur. So 1 times 32.06 grams per mole. Now what about the oxygens? So we've got 4 O's here, and we've got 5 O's here. So with this dot here, I want you to think of this as kind of like a plus sign. I'm just adding. The dot here means bound waters. They're called the waters of hydration. Now all this means you have 5 water molecules bound to the surface of this copper 2 sulfate crystal. So I don't want to multiply. I want you to think add. So I have 5 O's. So it's going to be 4 plus 5 more. It's going to be 9 O's total. So it's going to be 9 times 16. Hydrogens, we have, distribute this through, you have 10 H's. So 10 times 1.01. That's 10.10. 9 times 16. 9 times 16, that is 144. Okay. Add this all up. I have 63.55 plus 32.06 plus 144 plus 10.1. 63.55 plus 32.06 plus 144 plus 10.1. That gives us 249.71. 249.71 grams per mole. Alright, so that's how we find the molecular weights of a bunch of different compounds, or molar masses. So this is the basic idea of chart we're going to use. You want to calculate, go from molecules of A. Let's see, I rephrase it. Let's say you want to find molecules of A, but you're given the mass of A. Knowing what you're given, we can use the molecular weight to find moles. Then we can now use Avogadro's number to find molecules. We did the same thing in the last chapter involving basic atoms. So let's take a look at this problem here. Calculate the number of atoms in 25 grams of sodium metal. So 25.00 grams of Na. Now, had this been, say, sodium chloride, you'd know this is just a sodium chloride right here, and use the molecular weight of sodium chloride. But since this is just pure sodium metal, I just need to find the atomic weight of sodium metal. 1 mole of Na, and that's 22.99 grams of Na, and that came from the periodic table, where it's just 22.99 over here. If you can check your table, you can see that better than mine. Well, 1 mole of anything is 6.022 times 10 to the 23 of that item. Of course, that's going to be atoms of sodium. So 25, divide that by 22.99 times 6.022 times 10 to the 23rd. And we still get a number a little bit bigger than Avogadro's number, because 25 divided by 22 is more than 1. So we actually have more than a mole. So we got, now check sig figs. 25.00's got how many sig figs? Got 4 sig figs. So I'm going to round my answer to 4 sig figs. So 6.548 times 10 to the 23 atoms. Alright, so again, if this was a sodium chloride, we would just say we need the molecular weight of sodium chloride down here, and the problem would be exactly the same otherwise. Calculate the number of atoms of oxygen in 100 grams of H2SO4. It's a little bit different. 100 grams H2SO4. Now, something I want to point out here, 100 grams got how many sig figs? Okay, these last 2 zeros don't count because there's no decimal place shown. So my answer only has 1 sig fig. Only 1 sig fig. Alright, so 1 mole of H2SO4. I have to add up the atomic weights of this. Let's see, hydrogen will be 1.01 times 2, so 2.02 plus 32.06, that's the sulfur, plus 16 times 4 is 90, so we get 98.08. 98.08 grams. Now if we check our units here, grams cancel. Likewise in the last problem, grams canceled and moles canceled. So now we have moles of sulfuric acid. The question is, what's the atoms of O? Well, we could say for every 1 mole of sulfuric acid, we've got 4 4 moles of just oxygen. Because that's what the ratio says. For every 1 sulfuric acid, we get 4 O's. Now we end the problem like we did the last one. For every 1 mole of O is 6.022 times 10 to the 23 atoms of O. 100. Divide that by 98.08 times 4 times 6.022 times 10 to the 23rd. Round out the 1 sig fig. That is 2 times 10 to the 24. There we go. That's how we do that one. The calculator said 2.4559 times 10 to the 24. Round to the 1 sig fig, it's just 2 times 10 to the 24. Now here's when the problem goes backwards. Find number of grams of water in 2.50 times 10 to the 24 molecules of water. We'll start with what we have. 2.50 times 10 to the 24 molecules. So 1 mole of water is 6.022 times 10 to the 23 molecules. We want to find grams. Well, we know 1 mole of H2O. Now I need the molecular weight of water. Each oxygen is 16. Hydrogen will be 1.01 times 2. So overall it's 18.02 grams of water. So 2.5 times 10 to the 24, divide that by 6.022 times 10 to the 23, times 18.02. Now, how many sig figs do we need? 2.50's got 3 sig figs. So I end up getting 74.809. So 74.8 is the final answer. 74.8 grams of H2O. That's that one. Last one here. Calculate the number of grams of sodium. 5.00 times 10 to the 23 molecules of sodium carbonate. Now, what's sodium carbonate? Well, carbonate is CO3. Carbonate has a -2 charge. Sodium is a +1 charge, so therefore you need 2 sodiums. So Na2CO3. So you need to memorize these polyatomic ions to be successful with this. I need to convert this into moles first, because you can't go directly to what you're looking for. You need to get the moles first, and this is molecules. More specifically, it should say formula units, because this is ionic, but I'm not going to make a big deal about the terminology here. 1 mole of Na2CO3 is 6.022 times 10 to the 23 molecules. So now I got moles. I want to find grams of the sodium. Well, sodium carbonate's got 2 sodiums per 1 mole of the whole thing. So for every 1 mole of Na2CO3, you get 2 moles of Na. So now we can finish the problem off. 1 mole of Na is 22.99 grams, and you can solve that. And round this down to 3 sig figs. So 5 times 10 to the 23rd. Divide that by 6.022 times 10 to the 23rd. Double that, times 2. And then times 22.99. That gives us 38.2. 38.2 grams of Na. So if you had this many molecules of sodium carbonate, that's equivalent to having 38.2 grams of sodium. Alright, so how do we get the combustion problems? So basically, composition of compounds. Combustion's coming up in a second. So the idea here is, But if you know, we can calculate the percent mass of each element. If you know what the compound is. So basically, let's find the percent composition of sulfuric acid. Sulfuric acid is H2SO4. So the idea here is I want to find the percent of each component. We have H's, we have S's, and we have O's. So I need to find the molecular weight of this total. I think we found that earlier. Sulfuric acid has a molecular weight of 98.08. 98.08 is a molar mass of sulfuric acid, so we'll use that. Okay, so 98.08 grams per mole, that is the molar mass of sulfuric acid. So in order to find the percent hydrogen, it's going to be 2 times H, so 2 times 1.01, divide that by 98.08 times 100. So it's 2.02, because that's 1.01 times 2, so it's 2.02. Divide that by 98.08 times 100. This compound is 2.06. 2.06% hydrogen. I'm just going to round these to 2 decimal places. Sulfur. Well, there's only one sulfur. So it's going to be 32.06. That's the atomic weight of sulfur. We'll divide that by 98.08 times 100. So something around a third, thereabouts. 32.06. Divide that by 98.08 times 100. And you get 32.69. 32.69% S. In order to find the percent oxygen, at this point you could just take 100 and just subtract these off, and you'll get that. Or we can calculate like we did this now. Oxygen is 16, so 16 times 4, that's 64. Divide that by 98.08 times 100. 64, divide that by 98.08 times 100, and we get 65.25%. Oh. Now these should add up to 100%. They might not because of rounding issues. So each of these numbers should be rounded. So because of rounding, they may not add up to 100% exactly. So if we would have taken 100 and just subtracted 2.06, subtracted 32.69, what does that give us? Oh, I'm sorry. So 100 minus 2.06 minus 32.69. You get 65.25. Okay, this one worked fine. No issues here. You get exactly 100 either in both cases. But sometimes when you do this, you may get a number, if you add them all, it might be a little bit off depending on how rounding worked out. In this case, you got exactly 100%. And it'd be exactly the same. Finding percent composition. This you found because you knew what the formula already was. If you don't know what the formula is, we can use percent composition data to get to the empirical formula. So if you knew what this was, but you didn't know what the compound was, I can use this to find the empirical formula. Okay. Now the empirical formula is the simplest whole number ratio of a compound. It is not the ratio of the masses. It's the ratio of the moles. So, for example, if I gave you the compound H2O2, this is the molecular formula. Its empirical formula would be basically, if I can simplify this any further, Well, 2 divided by 2 is 1, so its empirical formula is just HO. So HO is the empirical formula of H2O2. Let's try something like water. The molecular formula for water is H2O. Can this be further simplified? No, I can't simplify this any farther, so water's empirical formula is also the same as the molecular formula. Let's try C2H4. C2H4 is the molecular formula. Can this be simplified? Yes, I can divide these all by 2, so its empirical formula is going to be CH2. Because 2 divided by 2 is 1, 4 divided by 2 is 2. So CH2 becomes the empirical formula of C2H4. What if I give you C4H8? This is the molecular formula. I divide both of these by 4. I get the empirical formula as CH2. So two different compounds can have the same empirical formula. Something to keep in mind. So percent composition data can get us to the empirical formula if we're going to follow a procedure to do that. Alright, so this is what we're going to do. Convert percentages in the mass. So if we're given percent composition data, we're going to make the assumption that we have a 100-gram sample, and therefore we can find that it'll allow us to figure out how many grams of each component we have. If you already know the mass of each component, we'll just skip that part and just use that directly. We're going to convert grams to moles, and then we're just going to divide it by the smallest to find number ratio of each. After doing this division step, if we end up getting fractions, we can multiply them by multipliers to get rid of the fractions. If you took me for Chem 1025, we did exactly the same steps. It's easier just to show some problems. Alright, I'll come back to this in a bit. So it's found that 11.57 grams of iron combines with 4.43 grams of oxygen. What is the empirical formula of the oxide? 11.57 grams. 11.57 grams of iron. And we have 4.43 grams of O. 4.43 grams of O. So the first thing we have to do, we're going to convert, since we're given the masses directly, we're going to use the masses we're given. We're going to divide these by the atomic weights to find moles of each. Iron has an atomic weight, we check the periodic table, of 55.85. Alright, so 11.57. Divide that by 55.85 equals 0.2072 moles of Fe. When you do these problems, I would keep 3 or 4 sig figs at minimum. Regardless of what you're given over here, since this is not the end of the question, I would keep more digits than what you need. 4.43 over 16, that is 0.2769. Again, I'm keeping more digits than what's required. Moles of O. Alright, once you've done that, we're going to divide by the smallest. Compare these numbers and pick the smallest one out. 0.20 is less than 0.27. Divide both of these by iron. If you do this, we're going to get 1 Fe. Moles are going to cancel, by the way. Moles cancel out, giving just numbers here. And 0.2769, divide that by 0.2072, that gives us 1.336. That's 1.33 essentially. 1.336 appropriate or thereabouts. O's. So this gives us a formula of FeO 1.336 thereabouts. Now, if I go back to my slides here, that's where it talks about the pseudo formula business unit subscripts. That's what we just did. Okay. Rephrase that. We're here. We're at number 4. We divided by the smallest and we got something. Now our numbers are not convenient. You can't have, a 0.336 of an atom. So we look at the numbers we're given. If the ratio, for example, is 0.5, in other words, it's 1, if something ends, for example, if it's like 1 to 1.5, if I multiply both of these by 2, you get rid of this fraction. If it's like 1 to 1.33 approximately, multiply both of these by 3, you get rid of this fraction. If it's 1 to 1.25 or 0.75, multiply both of these numbers by 4, it gets rid of the fraction. If they're already whole numbers, don't worry about this step. So if you look at what we have here, we've got 1, it's 1 to 1.33 essentially. Okay. That is basically by saying multiply by 3. So I'm going to multiply both of these by 3. Times 3 times 3. That gives me Fe 1 times 3 is 3, O 4. And that now is the empirical formula of this iron oxide. That's how we're going to do all these problems. Alright. Let's try the next one. Next one's a little bit different. You will find these same questions also in the Chemistry 1025 Survival Guide in Module 8. This part is still a review from last semester. This one's a little harder. What is the empirical formula of an oxide? 1.4 grams of nitrogen. So nitrogen of N. N2 is reacting with O2 to make NXOY. Our job is to find the values of X and Y. That's what we're trying to find. Now we're told we had 1.4 grams. 1.40 grams of nitrogen. That's reacting with oxygen to make an oxide. We're given the mass of the oxide. The oxide is 3.8 grams. Now when you think about this, when you do these problems, we're making the assumption that really this is 1.4 grams of N. And that's 3.80 grams of all of this. So we have to find the mass of just O. I have to find the mass of O that was used to make the oxide. Okay. So we have 1.40 grams of N. We're going to treat this all as monoatomic ions, atoms, molecules, even though they're not. We're going to treat them as monoatomic. So basically saying there's so many grams of N that we used. To find the mass of O, we'll do this by difference. 3.8 minus 1.40, that's 2.40. 2.40 grams of O. So if the problem is written like this, we're making oxide like this here, you need to figure out the mass of the oxygen by difference. At this point, we're going to follow the same steps as the last example. Oxygen is 16.00 grams per 1 mole. Nitrogen is 14.01 grams per 1 mole. 1.4. Divide that by 14.01, and that is 0.09993 moles of N. 2.4. Divide that by 16.01, and that gives us 0.1499. moles of O. Which one's smaller here? Nitrogen. So I'm going to divide both of these by nitrogen. That's the smallest. 0.0993. Divide that by 0.0993. Something divided by itself is 1. That equals 1 n. So divide 0.1499. Divide that by 0.0993. That is 1.5. 1.50. That gives us a formula of NO 1.5. So go back to the little chart. If it ends in 0.5, you multiply by 2. Multiply by 2. So multiply both these by 2. So multiply all of this, so times 2. So it's 1 times 2 is N2. 1.5 times 2 is 3. And that is the empirical formula here. I made N2O3. Now, can this be further simplified? No, I can't divide these by anything smaller, by anything to make them smaller. That gives us the empirical formula. We'll skip the third one. You can work that on your own. Determine the molecular formula of a compound with a molar mass of 60.10 grams per mole, percent composition of 39.97 grams of C, 13.41% H, 46.62% N. So in order to figure this out, it's a little different. Here we have to find the molecular formula. In order to do that, I have to find the empirical formula first. So we have 39.97%. Now this should add up to 100%. So we'll make the assumption we have 39.97 grams of C, 13.41 grams of H, and 46.62 grams of N. Same steps as before. Divided by the atomic weights to find moles. 1 mole of C, 12.01 grams, 1.01 grams per 1 mole of H, and we have 14.01 grams, 1 mole of N. Alright, so 39.97, divide that by 12.01, that is equal to 3.328 moles of C. 13.41, divide that by 1.01, that is 13.277. Mole of H, and 46.62, divide that by 14.01, that is 3.327 moles of N. I should have cut maybe a couple extra digits, an extra sig fig for each of these, but I didn't, but it won't make that much difference really. Alright, that gives us this information. Which one's smallest? Comparing C and N, notice they're both the same. 3.3, basically 3.33, 3.33, they're exactly the same. So I'll just pick one. Let's divide each of these by 3.3276. Just for consistency purposes, I'm going to call it 8. That's what this rounds to. 3.328 to be consistent. Alright, if you do that, so carbon's the same, N's the same, that's going to give us 1s. So that's going to give us 1C, 1N. So the question now is what's hydrogen? 13.277, divide that by 3.328, 3.98, 3.99, 3.99H. That's close enough to 4. That's 4. Okay. That gives us the empirical formula of CH4N. No fractions, no decimals. That's done. So that's the empirical formula. CH4N. Alright, now you want to find the molecular formula. So in order to do that, that's the part that I skipped back here. If you know what the true molecular weight is, this has to be given to you. And it is in this question. I take what's given, divide that by the empirical weight, which we can figure out now. That will tell us the multiplier factor. That will now tell us how to find the molecular formula. Whatever we get for n, I want to multiply that by the empirical formula. Let's do this here. So the molecular weight is 60.1. 60.10. That's the molecular weight. That's this number. That's what was given up here. That was that. We can divide this by the empirical weight. So I have 1 C, 4 H's, and 1 N. So 12.01. 4 H's. 4.04. That's 1.01 times 4 plus 14.01. That's the atomic weight for N. Add that up. 12.01 plus 4.04 plus 14.01 equals 30.06. Well, I'm not going to worry about the decimals here in this case, because you can clearly tell that the number on top was twice the biggest number on the bottom. 30 times 2 is 60. That's going to give us a value of 2. That's our n value. That's the n value in the prior slide we're talking about. So I'm going to take this 2, multiply it by, I'm going to multiply it by all this. That'll give us the molecular formula. So the molecular formula is going to be C2H8N2. So I have an empirical formula, call it EF, and I have MF. So that's how we do a problem like this. Alright, so I'm going to stop this video for now, and I'll come up and make a third video talking about the stuff that's specifically new to this chapter, to this class.